Okay, so base strength of amines, we're on page 11 of the topic booklet. And let's just remind ourselves what our the Bronsted-Lowry definition of acids and bases is. Well, let's do bases. Bronsted-Lowry definition of bases? Proton acceptor. So we just start with ammonia. We know that ammonia can use its lone pair to accept a proton, like that. And it's a weak base, so we'll use a reversible arrow and makes an H4+. Okay, so that's all fine. But I've used the curly arrow on purpose. We don't normally do curly arrows, do we, with Bronsted-Lowry bases? But I've used it on purpose because it kind of looks like a nucleophile now, doesn't it? In fact, if you think about it, being a base, being a proton donor is a bit like being a nucleophile. That's why we've got more than one definition of base. So we have Bronsted-Lowry definition, which is acids are proton donors and bases are proton acceptors. The Lewis definition of acids and bases is different. We've done Lewis acids and bases? Should have done it by now in transition metal chemistry. No? Well, you're looking at it. A Lewis base is a lone pair donor, which means a Lewis acid would become lone pair acceptor. Yeah, look at the H plus in the diagram. What's it doing? It's accepting a lone pair of electrons. And it's being an acid, of course, because it's donating itself as an H plus ion. So we've got an H plus donor, which is also a lone pair acceptor. Why would you see this in transition metal chemistry?
It's ligands.
Yeah, ligands, that's right. So if we've got a copper 2 plus ion and I stick a ammonia on there, then the ammonia's, basically doing the same thing. It's not hugely different, is it, in terms of what's going on there? It's just that for copper 2 plus, of course, there's a whole bunch of them around there, and probably some waters as well. I don't know what the geometry is for. We have a couple of waters there, don't we? There we go. There we are. So that's our copper 2 plus ammonia in excess thing. Well, it's the same principle, which is we've got bases or nucleophiles or ligands, whatever you want to call them, donating lone pairs of electrons. Okay, so keeping that in mind then, how does the ammonia change if I take off one of the hydrogens and stick on, say, an ethyl group? Obviously, when I say change, I mean it'll still do the same thing, right? It'll still donate a lone pair of electrons to the H+. It'll still act as a base, but will it be better at being a base, or will it be worse? Will it be a stronger base, essentially, or a weaker base? Just talk amongst yourselves, think about that for a moment, or alternatively, you could read page 11. If you don't want to read page 11, think about it. We'll go to page 11. Anyone want to share their thoughts? Tell us.
So carbons, they push the electron to towards nitrogen due to the positive inductive effect.
Okay, just hit pause there. Positive inductive effect. Okay. Let's just remind ourselves what the positive inductive effect is. Do you want to tell us what the positive inductive effect is?
Where all the electrons move to like one atom.
Yeah, when we're talking about positive inductive effect, we're specifically talking about alkyl groups, CH3s, C2H5s, whatever it is. So what is it that's going on there? Well, can you remember what causes that effect?
Is it will it be got to do like the delta positives and delta negatives?
Yeah.
And
So
move towards
yeah.
the delta negative region.
That's right. You're spot on. So differences in electronegativity. So carbon's ever so slightly more electronegative than hydrogen. So the hydrogens are all pushing electrons to a carbon, and then the carbon can shunt some of that electron charge down the line. So if we've got a chain of CH2s, whatever it is, CH3s, then we can shunt a little bit of electrical charge along that line. Where have we seen this before? Where does the positive inductive effect come in? I'll just give you a clue there. Where have we seen that before? In yes. Which bit of chemistry does that come up? What's the content that's associated with that carbocation?
Which one's more favourable?
Yeah, in what process? Which mechanism are we in? In?
Elimination.
It's not an elimination. Don't get a carbocation hanging around in elimination. It's the opposite process. It's the opposite of elimination. Electrophilic addition. That's great. So in the kind of the shot before that, we had a double bond. Okay, there it is. And we've got an HBr up here. Yeah, we have electrons coming from the double bond to the H and making a new carbon-hydrogen bond, and we've got a choice. It can either happen on that middle carbon there or on the end. We say the middle is favoured, or to be more precise, the secondary carbocation is stabilised by the positive inductive effect. Those 6 words, which make your answer really good. If we had the carbon on the end, it's only got sort of 1 positive inductive effect coming down the line. Carbocation's more stable if it's got 2. Okay, so that's where we've seen it before. Methyl groups or alkyl groups shunting electrons along to the carbon. In this case, carbon's got a full positive charge. If we shunt electrons down to it, that stabilizes a bit, makes it a slightly more likely to hang around for a minute, because this is almost certainly a reversible reaction and it could just go back. So the longer that intermediate hangs around, then the more likely it's got of reacting with the bromide, which must be knocking around in solution somewhere, and it's going to form a major product, favoured product. Okay, so that's that. So we've got the same situation here. We've got our ethyl group shunting electrons down to the nitrogen. Okay, so what? How does that affect nitrogen's ability to donate a lone pair? Better or worse? Stronger or weaker? Stronger. Because?
The electron densities towards the nitrogen.
Okay, so we've got
Makes it easier.
electron density towards the nitrogen. We're pushing electrons onto that nitrogen. That's going to make it more favourable for nitrogen to give away its electrons. At the end of the day, it's got to give up electrons and form an N plus instead of a C plus. We can sort of see that there. And this reaction's reversible as well. So the longer that can hang around, the better. So by the positive inductive effect, donating electrical charge to the nitrogen makes it easier for it to donate its lone pair. Let's just write that down. Positive inductive effect. Donates electrical charge okay. Stronger base. So what have we got? We've got ammonia, PKB, just a quick reminder, what's PKB? Let's do this one at a time. What's the K? Constant, which constant? There's a lot of constants. R is a constant, C is a constant. It's the, there's no acid constant. Capital K? Okay, equilibrium constant. KB, equilibrium constant for bases. The B is just like a tag to remind us which K we're talking about. We can have Ka for acids, Kc for concentrations, Kp for pressure. So Kb is the constant for bases. The little p, you've seen it before, pH, pKa, not percentage. What's pH? What's the definition of pH? This is not a hard question. Well, that's kind of the origin of the word, yes, but it's not what it means today to you, to us in chemistry. pH is not the concentration of H plus ions, it's minus log. Okay, so pH is minus log of H plus ions, then pKb is that would be POH. Come on, Joe, what have you got? So close. If pH is minus log of H plus, pKb is minus log of Kb. Okay. All right. So it just it takes our very big number, very small number, whatever it is, and turns it into an easier number to manipulate. Just like pH, bigger number, stronger base. So pKb, bigger number, stronger base. So if I put ethyl amine or amino ethane into that, it's got a P, maybe a 10.64. Goes up. Hooray! Theory and practice align. If I put another ethyl group on, so I have diethylamine, it's going to go up again. We've got 2 ethyl groups pushing in electron density. 10.73. I have to say I'm a little bit disappointed in diethylamine. It's not quite as high as I'd expect. I would have thought if ethyl goes up more than 1 notch on the pH scale, which remember is a factor of 10, then I would expect 2 to kind of do as much damage. In fact, if I put 3 ethyl groups on, it actually goes back down again. And the reason is solubility. If you can't dissolve an amine very well in water, it's going to be very hard for it to, do this kind of thing, because it needs to be an aqueous solution to do this kind of thing, to pick up an H+. So, yeah, if we keep stacking carbon groups on anything, it becomes less and less soluble. But what if we put a benzene ring on? Yeah, we know about benzene rings now. That does something very dramatic to the base strength. It seems to almost completely fall off. 4.62 is hardly a base at all. What's going on there? Why does a benzene ring mean the base strength plummets? Just before you answer that question, could you answer a different question, which is, what do we know about benzene rings? What do we know about this ring of 6 carbons that means that we draw it with a circle rather than 3 double bonds?
They create a ring with delocalized electrons.
Okay, so a ring of delocalized electrons, what we call the pi cloud. It's a sort of big donut sitting above and below the ring. And so that pi cloud of electrons is sort of swirling around, kind of washing machine style, in the ring there. And we've got another pair of electrons sitting up there. So what might happen to these pair of electrons with this swirling?
It'll move into the ring.
Yeah, they move into the ring, that's right. So we can imagine, and it's very difficult to draw this without it suddenly becoming sort of quite rude, but the delocalized electrons can sort of scoop up the lone pair of electrons there and kind of pull them down into the ring. And if they're pulled into the ring, then they're not up here anymore, sitting on the nitrogen. If they're not sitting on the nitrogen, they can't be donated. So benzene, we've got an opposite problem. The lone pair of electrons becomes delocalized in the ring, so is not available to be donated. Okay. Smashed it.